Thanks, Sasi, and thanks to the organizers for putting up this very nice conference, celebrating the works of Sriram and felicitating him. I'm actually a student of Sriram. I did my PhD with Sriram. And with all these allures of active matter, believe it or not, I was working with Sriram on Glassy dynamics. So everyone around me was working on active matter, and I was working on Glassy dynamics, specifically mode coupling theory. So today I thought I will combine these two aspects and present some unusual result in a Confluent epithelial monolayer, where from the perspective of the mode coupling theory. So in the course of this work, we have collaborated with several people. Some of them are here, Chandan, Madan, and possibly Rajesh, maybe online. And this work is done by student Sovik, Somitro, and Satyam. So let's start with a brief definition of what is glass. If you quench the temperature of a liquid below its melting point, it usually goes to the crystalline phase, which is the thermodynamically stable phase. But crystallization is a time-consuming process. If you do not allow the crystallization to happen somehow, for example, by cooling fast or polydispersity, then the structure remains similar as that of a liquid, but the relaxation time increases quite fast. And eventually, beyond a certain point, it becomes impossible to actually keep the system equilibrated, and that is known as the glass. A working definition of glass is when the relaxation time becomes of the order of 100 to 1000 seconds. Now, if you take a snapshot of a liquid and that of a glass, they look nearly identical. There is almost no way to differentiate between them, but their dynamics are quite different. In the high temperature liquid phase, if you look at the autocorrelation function, it decays quite fast, exponentially fast. And as you go towards the glass phase, the decay becomes complicated. It shows a two-step relaxation scenario. It first decays towards a plateau and then from the plateau towards zero. This is known as the angel plot, where one represents the viscosity or the log of the viscosity or relaxation time as a function of Tg over T, and this shows this type of characteristic phenomena. For some of the system, it shows this diagonal straight type of line. This is the Arrhenius system, and for some others, it deviates from this line, and those are known as the fragile glasses. There is another interesting aspect of glassy system, and this is known as the dynamical heterogeneity. So this is the existence of slow and fast moving regions at the same system at the same time. Now, this is an interesting problem, and it remains unsolved for a long time in statistical physics. There are several theories to try and understand what is the mechanism of the glassy dynamics, and this is not an exhaustive list. There are several others. Some of the theories, for example, free volume theory, mode coupling theory, random fast order transition theory, etc. So all of these theories, they fail at some point or the other to describe this system. And because it's an important problem, it continues to be developed various other theories. It's important because it appears in many facets, both in real life as well as in scientific problem. For example, in window glass, glass utensils, artwork, etc., and both in hard and soft condensed matter physics. But recently, it has been shown that in many biological systems, this glass-like aspect is observed. And this is what I'm going to give three class of systems. So the first class is the cellular cytoplasm. In 2001, the group of Friedberg, they showed that the cellular cytoplasm behaves as a glassy material existing close to a glass transition. And several works followed, showing that the cellular cytoplasm indeed behaves like a glassy system. For example, the mean square displacement shows the characteristics subdiffusive to diffusive behavior. The Van Hoff function shows non-Gaussian behavior. And this is the angel plot like plot where viscosity as a function of phi over phi g, where phi is the density, it shows the characteristic strong to fragile type of behavior. And this is an in vitro cellular cytoplasm system. This is another paper showing the glass-like properties in the bacterial cellular cytoplasm, etc., etc. Now, this is the second type of system, and this is something that Frank was talking about yesterday. This is the biomolecular condensers. So cells need to organize their biochemical reactions. They do it via compartmentalization. There are two types of compartments. So one of them have membrane and others do not have membrane. In 2009, the group of Frank, Tony Hyman, Brangwine, etc., they showed that these non-membrane bound compartments, they form via phase separation. And more recently, several groups have shown that the dynamical properties of these protein condensate, these biomolecular condensate, they have glass-like properties. For example, I'm paraphrasing from this paper by Frank's group. that the viscosity strongly increases with their age, but there is no significant change in structure at the same time. So what they conclude that the protein condensates can be soft glassy materials with age-dependent materials. So there are some figures from that same paper showing the mean square displacement, the subdiffusive to diffusive-like behavior, and the loss modulus and storage modulus showing the characteristic sort of crossover. And this is another result from the group of pure energy showing that the viscosity increases quite rapidly with changing composition and this phase separation strength. This is another class of material where, or system, where showing that the collective motion in confluent cellular monolayer, they show glass-like behavior. So here, this is showing the dynamic heterogeneity length scale that is increasing as cell number density increases. Also, the relaxation time increases with number density. The 2-point and the 4-point correlation function, they also show glass-like behavior. And so the glassiness in this biological system, they are crucial for many processes. For example, they determine the transport and the mechanical properties of the cellular cytoplasm. They are also relevant for various processes such as wound healing, cancer progression, embryogenesis, pattern formation, etc. And these systems are quite fascinating examples. They enrich the field of the original glass transition problem, and they also extend the extent and scope of the problem. And understanding the glassy dynamics in this system has, of course, the biological importance, but they also promises deeper insights on various aspects of the equilibrium problem itself. And from now onwards, because of the interest of time, I'll focus on the glassy dynamics in the confluent systems. Now, for a brief simplified overview of the confluent system, for a cell, for all practical purpose, the mechanical properties of a cell given by a thin layer of cytoplasm known as the actomyosin cortex, and then there are different cell-cell adhesion via different adhesion molecules, also tight junction molecules, and then they can also interact with the substrate via focal adhesion. One particular aspect of these systems that I'm going to talk about, this confluent system, that they are always confluent, means these particles always cover the entire space. Packing fraction remains unity at all times, and it cannot be a control parameter for these systems. Another experimental observation is that the height of the cells remains nearly constant at a particular time, and it allows a two-dimensional description. So the two-dimensional description basically has two aspects. One is that they are described, there is an energy function, and this energy function has two parts. This is the area, so this is a two-dimensional monolayer, this is area minus A naught square. So this particular term comes because you can consider the cellular cytoplasm as a incompressible fluid, and the height remains nearly constant. So these two aspects one can write as a area constant, where lambda A is the strength of that constant, and this is the perimeter constant. Pi is the perimeter of the cell, and P naught is a parameter. This term one can write as sum of two parts. So this first part gives the property of the cellular cortex, and the second part gives the adhesion property, cell-cell adhesion. And these two constants can be written in this perimeter constant term, where lambda p gives another constant of this known as the perimeter moduli. Now, given this energy function, one needs a temperature to simulate, and this temperature has a complicated status in the biological system. It actually includes all active processes as well as equilibrium temperature, but within these models, they have the status of equilibrium temperature. So I'll take it as a equilibrium temperature. Now, given this energy function, one needs defined confluent models. And these models, they represent the cells as polygons. There are mainly two types of models. One is continuum model, such as the vertex model, Voronoi model, and then there are discrete lattice-based model known as the cellular pots model on various types of lattices. And these are some snapshots from our simulation. From the Voronoi model, this is the cellular pots model, and this is a movie from the vertex model, and this is a movie from the experiment that we are doing on the MDCK monolayer. Now, I'll analyze the glassy dynamics in this system from the theoretical perspective. So let's go through briefly the one of the popular theory known as the random first order transition theory. So within this theory, the system comprises of mosaics of various states. So each of these mosaics, they represent one particular state. Now, if you consider a system of length, say r, the way it can go from one state to another it is a competition of two terms, one bulk term and one surface term. So this bulk term basically is the gain in free energy because it wants to escape from one state to the other. And the surface term, this represents the surface mismatch energy. Now here note that this theta, this SD is for the surface area for a unit sphere, but theta is not d minus 1. It can be defined from d minus 1 within this theory. Now within arithmetic theory, this escape from one state to the other for the mosaic, it is given, it is entropic in nature, and therefore this f, the small f comes as TSC, where SC is known as the configurational entropy. Now I can minimize this delta f with respect to R and then get a typical length scale for these mosaics, and this will have this particular expression. Okay, now there is one important aspect for arithmetic theory, and this is the existence of Cosman temperature. What it says that there is a finite temperature at which the configurational entropy vanishes, and the entire theory is based on that particular aspect. So I can go close to Tk and expand Sc as linear T minus Tk for T greater than Tk, but it should be 0 for T less than Tk. So this is the thermodynamic transition that is within the arithmetic theory. Now considering a barrier crossing type of dynamics, I can write down the relaxation time as this e to the power minus delta naught xi to the power psi divided by t, where xi is the typical length scale and psi is another exponent. And using these expression from these two lines, I can write down the relaxation time as a function c over t minus tk to the power this exponent, which is a combination of psi divided by d minus theta. Now these exponents are very hard to compute, and till now there is no calculation exists to get psi, but for theta there are different calculations, but there are different possible choices that has been argued, and one such possible choice, that is psi equals to theta equals to d by 2. So in 2 dimensions it becomes d minus 1, but in 3 dimensions it will be different from d minus 1, the exponent theta. And with this choice, this combination becomes independent and becomes 1. Now the way to extend it, there is a phenomenological way to extend this particular prescription for confluent system. For confluent system, we have this interaction given by this energy function, where P naught appears here, that gives the intercellular interaction potential. So it's a parameter that parameterizes the intercellular interaction. And now both the configurational entropy and the surface configuration entropy, they will be given by the interaction potential. So I can write down a interaction potential which depends on P naught, and then expand it very close to a reference P naught, which is P naught reference, and keep only linear order terms, and then go through the similar argument that I was going through in the last slide, and write down the relaxation time as a function of something like this, where E, F, P naught reference, Tk and chi, they are all constant that one needs to calculate. Now arithmetic theory in principle provides a way to calculate all of these quantities from a microscopic calculation, but that's actually very hard. We take a different approach. What we do, we take a set of data and fit this expression and calculate all these parameters. And once these parameters are fixed within the theory, then there is no free parameters within the theory. Now you can actually compare the theoretical result with the simulation data. And this is what I'm going to show in the next few slides, and more details can be found in these two papers. And these are some comparison with a simulation from cellular POTS model. And here, this is the relaxation time as a function of temperature. So with one set of simulation data, we have obtained these values for those 5 parameters that I was talking about. And given these values, I just plot this particular expression log of tau and, sorry. Okay, so I plot this relaxation time as a function of temperature. The lines are this plot of this function, and the symbols are the simulation data, and they seem to work quite well. This is another representation of the same data as the angel plot representation, where log tau as a function of Tg over T. One can also compute kinetic fragility, whose definition is given here, and we also calculated that. And the symbols are the simulation data, and the lines are the line is the theoretical plot. That also seem to agree quite well. Now, till now, what I have talked about, there is no. Okay, so. This doesn't work. So till now, what I have talked about, there is no self-propulsion into any of the description. One can also include self-propulsion, and we have done it. So self-propulsion we already included into the particulate models, and some of the papers I have listed here. But in this Confluent system, it appears as this particular term here, and this is the contribution due to self-propulsion. There are more details that I am skipping here. We have also compared it with the simulation data, with existing simulation data from the seminal paper by Max, Cristina, Marchetti, Manning, etc. And this fit we are using to fix different parameter values, and then these are the comparison. So these are for different values of dr, these are the phase diagram for different values of v0 in the p0 dr plot, and this is the three-dimensional phase diagram that also looks quite similar to what they have in that simulation paper. Okay, so till now what I have described, there is nothing unusual. So there is the simulation system, and then there is the theoretical description, and now I will highlight what is the unusual part in this entire result. If you notice the angel plot for particulate system, the viscosity is given as Tg over T, and if you look, so there is this diagonal line known as the Arrhenius line. If for the system the curve falls below this diagonal line, those systems known as super Arrhenius, and if it falls above, they are known as sub Arrhenius. For particulate system, mostly one finds super Arrhenius behavior, so these curves will fall below this line. But for a Confluent system, the scenario is different, and what one finds that most of the system one finds the sub-Arrhenius behavior. For this is the result for the cellular POTS model, and this is the result for the Varanasi model that I have taken from this paper by Sushman, Matteo, Cristina, Marchetti, and Manning, and they have also similar result for the Vertex model as well. So for the Confluent system, the behavior seems to be sub-Arrhenius. Now why is this unusual is the following, that when we fit this data with the RFOT expression, there is a TK effective Cosman temperature, and for the sub-Arrhenius behavior, that effective parameter needs to become negative. Now, if it becomes negative, what it means that even at zero temperature, there is no divergence of the viscosity. What it means that this thermodynamic transition that this theory is based on does not exist in this regime. And therefore, strictly speaking, within this regime, the RFOT theory should not apply. What you also find that if you go to lower P0 and at low P0, all these systems you also find super Arrhenius behavior. So there is a regime where the RFOT theory actually applies, but not in the sub-Arrhenius behavior regime. So in the cellular POTS model, in the Varanasi model, in the Vertex model, when we simulate at even lower values of P0, we find that the behavior becomes super Arrhenius, and in this regime, the theory should apply as usual for the particulate systems. Now, going back to the sub-Arrhenius regime, why is this, what is the implication? So it is possible that there is no real divergence of the relaxation time and the viscosity, and it's not actually a glass. So therefore, one should not apply any type of glass theories for this regime. But in the last decade or so, there are several works that have shown that the system actually shows glass-like properties. Even in the sub-Arrhenius regime, this is glassy. So it is the second possibility is that the relaxation time indeed diverges, but it diverges different or slower than exponential. We think it is the second, and we have reasons to believe there are several of them. I'll just explain one of them. So in a completely different aspect, we are trying to understand some static properties, which is cell shape variability in confluent epithelial monolayer. And this work is motivated by Friedberg's group, who showed some unusual properties, some universal aspects in the cell shape variability in a confluent epithelial monolayer. What they showed that when they plot the probability distribution of the aspect ratio, which characterizes the cell shape, they find some behavior. But when they plot this particular quantity x, which is the ratio of aspect ratio minus 1 divided by average aspect ratio minus 1, they find that all this behavior seems to be same for diverse epithelial system. Second, they find that the standard deviation of the distribution as a function of the average aspect ratio that follows a particular curve for diverse epithelial systems. We developed a particular theoretical description for this based on this confluent system. So this is the probability distribution function, and what we find that all the system specific details, they get combined into a particular parameter, and that leads to these universal properties, and one can find more detail in this paper. But what I want to highlight for the purpose of this talk is the following, that when we plot standard deviation as a function of the average aspect ratio, and If we follow each of the points, what we see that as the dynamics becomes slower, in this plot the points moves towards the origin. So this also happens in our simulation, in our theory and simulation experiment in all of them. We can also characterize the relaxation time in terms of this particular parameter alpha. So what it shows that alpha that characterizes the static properties of the Confluent system that also can characterize the dynamic properties of the system. So dynamics and static for the Confluent system are quite strongly coupled even in the Glassy regime. And this is quite non-trivial because if you look at the equilibrium Glassy system, one of the aspects is that the extreme dynamical slowing down without much change in the static properties. Also to paraphrase from the Glassy properties for the biomolecular condensates, the viscosity strongly increases with age, but there is no significant differences in the structure. So this is what one would expect, and this is what most of the theories of glasses tries to explain, how the dynamic property, the transport property or the viscosity relaxation time increases so rapidly without much change in the static properties. But in the Confluent system, this is quite different. It seems that the dynamics and the statics are quite strongly correlated. And there is one particular theory that actually proposes precisely the same, and this is known as the mode coupling theory. So just briefly, the mode coupling theory gives an equation of motion. It gives an equation of motion for the time-dependent density autocorrelation function. It allows an analytical calculation, and this makes this theory quite popular. Despite the fact that the theory for the particulate system actually is applicable only a very tiny regime. It fails very close to the glass transition, even above the glass transition temperature. Despite that, it remains quite popular. It is an elegant theory, but the applicability is very narrow. But one crucial feature of the theory is that it requires only the static property as input, and with the static property, the structure factor, radial distribution function, etc., it can give the dynamics of the system. So this is what we are going to do. We will take the static properties of the Confluent system we'll give them as input to mode coupling theory, and we get the dynamics. We'll also calculate the dynamics from the simulation, and then we can compare the two. So we did it for the vertex model. We calculate the radial distribution function and the static structure factor from the vertex model simulation. So these are the static structure factor for various different temperature and different P naught. And we give this information as input to mode coupling theory and then get the dynamics from the MCT. We also obtain the dynamics from the simulation, and then we will compare how MCT works for the Confluent system. And this is one of the fast comparison. Within mode coupling theory, we get the 2-point correlation function, something like this. From the simulation, we get it like this. So one of the prediction of mode coupling theory is the time temperature superposition principle. What it means that if you scale time with relaxation time, you will see a data collapse to a master curve in the alpha relaxation time. So this is also is observed in the simulation as well, which is shown in the right. And this is another comparison of mode coupling theory with the simulation. So mode coupling theory predicts a power law divergence for the relaxation time. So if you plot the relaxation time as a function of t minus tmct in the log-log plot, you would get a straight line with particular slope. And this is what we see. So within mode coupling theory, you will always get a straight line because this is exact, and with a exponent that will depend on the system. So here it is 1.5. Usually in the particulate system, what happens that you do get this straight line within a particular regime, but it deviates from the straight line after some certain temperature. But in the Confluent system, what we find that in the subharmonious regime, the straight line seems quite well behaved. It is for all the data that we could get, it seems to follow the straight line. Also, this exponent in the particulate system, even when there is this straight line in the log-log plot, the exponent can be defined. Here we see the exact same exponent in the subharmonious regime. As we go to low P-naught regime, the dynamics become superharmonious, and then it becomes same as the particulate system. So in the superharmonious regime, we get the exponent from MCT 1.4, but in the simulation we get 1. So there the comparison becomes weaker. And this is the angel plot representation of the same data. So in the angel plot also, these lines are the mode coupling theory result, and the symbols are the simulation data. So currently we are also now testing these aspects in experiment on MDCK monolayer, and so there are some primary data it seems to suggest something similar that we see in the simulation as well. So these are the static radial distribution function, and this is the dynamics, and it seems to corroborate each other. But this is really primary data, and we need to test it further. So to conclude, Confluent system have both sub and subarrhenius regime, and in the subarrhenius regime, something strange happened. RFOT theory fails in the subarrhenius regime where MCT seems to work. Usually you see the other way around. Usually in the Glassy system, there is a regime where MCT usually fails and RFOT theory seems to continue to work. But here it seems the opposite, and this is one of the, in fact, I would go one step further and I would say that the subarrhenius regime seems to be quite ideally suited for this particular theory, the mode coupling theory, for this Confluent system. So this is a summarization of this result, that in the low P0 regime, the dynamics is subarrhenius. So in this regime, this activated barrier crossing type of dynamics is valid, and the RFOT theory seems to work. MCT seems to become worse in this low P0 regime. In the large P0 regime, one finds the subarrhenius regime. In this regime, RFOT doesn't seem to work, but the mode coupling theory, which has this structured dynamics feedback mechanism giving the relaxation dynamics, that seems to be more prevalent. So, thank you.
Questions for Saroj? Yeah.
Hi, thank you for the talk and for awakening my glassy past. So, how the two temperatures, the TK of the random first order transition and the TC of mode coupling, compare with each other?
Okay, so
normally TK is much lower than TC, right?
TK is much lower than TC. That so in the subarrhenius regime, it is complicated because the fit with the RFOT theory is not that good either. But in the subarrhenius regime, that seems to be there. The TMCT is higher than TK. So that aspect also seems to be there in the subarrhenius regime.
Because I'm very surprised that you use MCT to describe the subarrhenius regime, because normally MTC is divided to give a very strong increase of the relaxation time. So it was really...
MCT is power law, right?
Yeah, I know, power law, but I mean, the divergence is so much before TK that, I mean, the increase is very, very strong. So anyway, it works. So even in the subarrhenius, you have a TC which is rather high.
Yeah, so the subarrhenius regime, there are still things that we need to understand. Eventually what happens, and this is very strange that we still don't understand, the TC, when we feed the simulation data, that temperature eventually becomes higher than TMCT. And this I'm quite puzzled why that happens. Yeah.
Okay.
So that we need to understand.
Okay, thanks.
I don't see any more hands. So thank you very much, Saroj.